All right, everybody, welcome. Thank you for joining us in this different space today. Before I begin, I would like to acknowledge that we're in the territory of the Beothuk, and the Newfoundland Island is a territory of the Beothuk and Mi'kmaq. I would also like to recognize the Inuit of Nunatsiavut and Inutuhavut, and the Innu of Nitassinan and their ancestors as the original peoples of Labrador. Together, we strive for respectful relationships with all peoples on this land as we move forward towards collective healing and true reconciliation, and ultimately honor this beautiful place together. So before we get to introducing our speaker, I'm just going to give Charlie the floor for a second.
Yeah, hi. So I think most of you know me. I'm Charlie Mather. I work in the geography department. I just wanted to introduce Samson Aforeki. You can raise your hand here. So Samson's he's new to us. He's a postdoctoral fellow working at SINTEF in Norway. That's in Trondheim. Well, the SINTEF has offices all across Norway. He's part of a big project looking at new development licenses in aquaculture that are moving aquaculture offshore for environmental reasons. He's going to be here with us until February. He's in the sort of GIS lab area. Whereas I wanted to just give him a good welcome to the geography department, and he'll be interacting with us here in the department until February next year. That's
welcome. So our wonderful speaker today is Dr. Joseph Daraio. He's going to be presenting on integrated approach to climate change, adaptation, and resilient infrastructure. Joe has been at MUN since 2015 and is an associate professor in the Department of Civil Engineering. He earned his PhD in Civil and Environmental Engineering at the University of Iowa in 2009. He received his bachelor's degree in in environmental and forest biology from SUNY, College of Environmental Science and Forestry. He has a slew of master's degrees in biology, philosophy, and environmental engineering, so that's maybe what the integrated piece comes from. His primary interests include the assessment of climate change impacts, on natural and built infrastructure systems. His research is focused on developing new methods with which to incorporate climate change uncertainty into infrastructure design. Prior to joining Memorial, he was an assistant professor of water resources engineering at Rowan University in New Jersey, where he worked on the potential impacts of climate change on local water resources. So welcome so much, Joe. Thank you.
So thank you for the invitation. Thank you for having me here. I'm happy to report I am now a Canadian citizen too. So it was a little unusual taking an oath to the Queen, but different. I've been doing a lot of work, but I don't have a lot of really good results to report, which is what I was originally going to do. But I thought instead I'd kind of go over how I approach climate change adaptation and moving towards resilient infrastructure, which really is it's really multidisciplinary. So this is in part kind of a way to reach out to everybody here as well for potential collaboration as moving forward. So while I am an engineer, my background is broader, so I bring a little bit of a broader perspective than you might expect from an engineering point of view. I'd like to start, again, I will be speaking from the engineering perspective, and some of you who know me know some of my thoughts about engineers in general, but I am coming as a diplomat from the engineering profession. Starting with what the American Society for Civil Engineers call to action, and I will say that CSE, the Canadian Society for Civil Engineering, was a part of this. They came out and they work closely together, actually. So this is ASC. This really represents North America. And it goes as this, so whereas civil engineers provide essential infrastructure, that infrastructure is inadequate and dangerously deteriorating, and this is more so the case in the US than in Canada, though Canada is doing better, there are still major issues. The availability of resources and future conditions are highly uncertain. So when current approaches, practices, and standards do not address the full range of societal needs. So therefore, civil engineering practice must be transformed. The SE is taking responsibility to lead the charge with the goals is to transform how infrastructure is conceived, delivered, and operate to enable a sustainable future. Establish ASE as a trusted leader, and then they have the Institute for Sustainable Infrastructure. Envision's used in Canada as well. Is connected strongly with CSE and what engineers are doing throughout Canada as well as the United States. And then this is, to me, a really big one, expand the capacity of civil engineers to create relationships of trust and respect. So this is the ASCE's call. And so coming from this perspective, it's kind of how I view infrastructure. So let's talk about infrastructure. So it seems like it might be easy to define and talk about, but from a civil engineering perspective, it's central to where we are. It is really all areas of civil engineering have some kind of environmental aspects, some kind of environmental loading that's going to be impacted in some way, shape, or form by climate change. So civil engineers are in a really important position to make strong contributions to climate change and resilient infrastructure. But again, I like to think about this from the start. So Ken, you may have heard of this. Our former department head, it's his joke, so I'm going to give him credit. Said that civil engineering is the second oldest profession. So, there's many of you may have heard of Donald Worcester, who's written about one of the things he talks about is Carl Wittfogel's thesis of hydraulic civilizations. The hydraulic civilizations were the start of centralized power, and really the start of development of the state. And so, that's one way of looking at these big irrigation systems as well. A big part of where we are today in terms of civilization. If I would highlight the civil part, right? Civilization is in some sense is based on hydraulics. And really this term infrastructure comes from, it's a French word, and it's got a military basis. And I bring up the Roman road systems because without the infrastructure that the Romans had, Roman Empire would not have had the expanse that it did. And as we know, the Roman roads, the Newfoundland roads were built to the same standards as the Roman roads were. Because ours will definitely last 2,000 years, I think, without question. But what is infrastructure? So I asked this to my students. I'm going to ask you, can you define infrastructure? Feel free to yell something out. Maybe tell somebody, what's infrastructure?
What's under the hood?
Yeah. That's an easy way of putting it, right? Well, my students always say, bridge. Yeah. That's infrastructure. A culvert, that's infrastructure. Well, those are pieces of infrastructure. I don't know of any really clear definition. You can probably find one. I didn't look up a dictionary definition, but this is probably the best presentation of defining infrastructure from Paul Edwards' book, A Vast Machine. It's really about where we are in terms of global, our general circulation models and the infrastructure that was involved in getting to where we are to get this knowledge. He has a really good introduction and discussion of infrastructure. And this is not just civil infrastructure, this is all kinds of infrastructure. Information, cyber, electronics, energy, all share these characteristics. So when thinking about resilient infrastructure, just, like I'm going to refer to a culvert quite a bit in this talk, just for simplification, right? So a culvert is, it's that water flowing under your roadway, whatever the case may be, that's your culvert. They're all over the place. You don't notice them until they're not there anymore. So if we think about, the details of these terms, so embeddedness, so infrastructure, and again, this applies to all infrastructure, but I'm focusing here on the civil parts. Infrastructure is sunk inside of other structures, social arrangements, and technologies. Just this here, I don't know if anybody's been to Istanbul. Oops, wrong button. Maybe out of that. Hit the top button instead of the lower button. If anybody's been to Istanbul and seen this, this is under the main old part of the city. This is Medusa's head. It's upside down because if it's upside down, it won't turn into stone. So you can look at it when it's upside down. But I always found this amazing, dating back to Roman times, that this cistern was I have it here because it's literally sunk underneath the city. So that's why I've got it here. But it's just amazing to me because you don't even know it's there. Right? It's not functional anymore. Infrastructure has a really broad reach. It goes well beyond any one event, one thing, or a local practice. This here, I think this here is the largest freestanding bridge pier in the world. It's over 300 meters tall. I think it's quite a beautiful bridge, quite frankly. Infrastructure is taken for granted. So, and this is interesting to me, so outsiders take infrastructure as something to be learned about. And so you come to a new area, you have to learn and become familiar with the infrastructure. This is most apparent when you think about, if you go to the UK, you have to drive on the left. It's a simple change, but you have to learn how to adjust to that. And that's just one example of that. And then of course, Holland and the Netherlands wouldn't exist without keeping the ocean. And I spent some time in Holland, and there's something, I wasn't there long enough to really understand it fully, but there's something about, they're a hydraulic civilization. They're so proud of their hydraulics. I was fortunate enough to work at Delft Hydraulics. They're leaders in the world in this. It's transparent to use. You don't reinvent it or reassemble it each time, but it invisibly supports tasks. At one point in time when this was built, the CN Tower was the tallest structure in the world. Not anymore, of course. That's the Burj Khalifa, and that's still the case now. It links with conventions of practice. It's shaped by conventions of the community of practice. The Confederation Bridge, I think, is the largest in the cold regions that is affected by ice. The largest bridge extended by ice. So that's kind of significance of all those pieces of infrastructure I put up there. Now, getting kind of closer to home now, infrastructure embodies standards, right? It becomes transparent because it fits into other infrastructure, and is standardized. You go to most places, you don't realize that a lot of water bodies have control structures on them, so they become part of an infrastructure system. They're controlled, just like kitty bit. So, and it's built on an installed base, so it inherits the strength and limitations of its base. And I mentioned driving on the left. So downtown St. John's, the way the roads are can be thought. If you think about it in terms of prior to Confederation, everybody drove on the left. So the stuff that doesn't make sense in St. John's, a lot of that in downtown is because, it was developed initially because everybody drove on the left. Now you switch to driving on the right, things don't work anymore. So I found that to be really, really interesting as well. And then of course you don't notice it until it fails. You don't know what's there until it's not there anymore. And then another thing that's really, really important is it's layered, it's complex, and it's got to be repaired piece by piece. And this makes change hard, right? It makes change more challenging in these types of infrastructure systems because you can only change one piece at a time. So that's kind of just to kind of get you thinking about the complexity involved already when you talk about any kind of infrastructure system. Now talk about a culvert because it's simple, but it's part of a larger system. So let's talk more about sustainability, resilience, and adaptation. They're all linked terms. I don't think you can talk about one without the other. So this now is kind of, I think, how I think about these issues when I'm thinking about resilience in particular, right? So we're going to lead up to adaptation. So starting again with ASCE, their definition of sustainability is about the triple bottom line. You know, and I won't go over this in any detail, but I like this because their principle is for sustainable development is doing the right project and doing the project right. So that's the key. So we got to do the right types of projects for sustainability. So this is the famous definition, right? Sustainable development meets the needs of the present without compromising the ability of future generations to meet their own needs, and then full stop. That's what you see as a definition of sustainability. If you continue to read that, it also says sustainable development is not a fixed state of harmony, but rather a process of change in which exploitation of resources, direction of investments, orientation of technological development, institutional change are made consistent with future as well as present needs. This is so key, I think, and overlooked when we talk about sustainability, especially sustainable development. I used to think it was an oxymoron, but I think sustainable growth is an oxymoron, but sustainable development is not. Development can be done in a sustainable way. To me, that this isn't stressed more is always been a little troubling. But I think this is key, right? Jeffrey Sachs, who's written quite a bit on sustainability, talked about sustainability as a way of looking at the world and a way of describing shared aspirations for a decent life. So it's both analytic and normative. So you know, you can talk about life cycle assessment and those technical and analytical aspects of sustainability. But we're really going beyond that. You know, that's not what we're talking about. We're talking about how do we change the way of thinking and the approach. So, you know, and as it becomes more of a normative way to see the world. So again, it's a way to understand the world, you know, because the world is a complex interaction of economic, social, environmental, and political systems. And then also called a world, or the German term Weltanschauung, which I think doesn't translate quite frankly into English, but anyway, it's normal, right? And I think that's important. And it's again, this is where I come from. This is how I try to think about. Really, honestly, when I'm doing a lot of my work, I'm trying to think about it from this perspective. It's not always easy to do. So here we are. We've got our 3 pillars of sustainability. We're sustainable in that mix, and then you know what happens in those other areas. I've seen a lot of different versions of this. This is really weak. Let's call it weak sustainability. This is in a lot of ways where we are, but perhaps this is where we should be going into what's more of a strong sustainability framework, where we're integrated. We don't have separate areas. Everything's part and part. This is, I believe, a more true picture of how things are in order to get the sustainability. So resilience is a key part of this, of course, and it's closely linked, and it's part of the definition of strong sustainability. So if you don't know Brian Norton's a philosopher. He was at Georgia Tech, and he was in really their environmental policy program. He's written quite a bit about sustainability. He said, well, natural resources provide materials and services, and weak sustainability works on the assumption that we can replace or duplicate natural materials and services with manufacturing goods and services. Seems a little bit, seems quite right. But from a strong sustainability perspective, natural materials and services cannot be duplicated, and that's really it's a big difference. It's just words, but it's also meaningfully big difference. So from Norton's perspective, sustainable living will occur when a pattern of individual choices maintains integrity and resilience of the place the community inhabits, which I really like that way of thinking. And the other aspect is that it's, you know, thinking in terms of resilience is thinking in terms of systems. So you can't think about that culvert, make a change to that culvert, and say now you're building resilience. Make it bigger doesn't mean you're more resilient. It means you have a bigger culvert. That's all it means. All right, so I want to talk a little bit more about resilience. Everybody's got a sense of it from their own personal psychological perspectives, but I like to focus on ecological and evolutionary resilience and compare that to engineering resilience, and talk about some of the difference. So, kind of started from hauling, and this is a purely and kind of an ecosystems view and also applies evolutionary. So the magnitude of a disturbance that can be absorbed before the system changes its structure. So you're resilient up to a point, you reach a threshold, and the system is thrown out of balance. And it's a natural cycle. So again, think of this from ecological succession, or from an evolutionary perspective, in particular, natural systems are resilient. Other definitions, same kind of thing, the ability of a system to return to an equilibrium or steady state after a disturbance. Of course, with climate change, we have changing thresholds. So a resilient system can be pushed, but it's going to fall back into its equilibrium state. Once you pass that threshold, well, in this case, we don't know what's going to happen. Then we get into a new state. So we got a threshold tipping point. So we're here. If we get pushed too far, then we go over the tipping point, and we get into a new system state. We could have a changing tipping point, and so we have a shifting. I'll think of this as a resilience landscape, and I'll talk a little bit more about this as we move forward until we get to a new system state. So engineering resilience is, okay, let's constrain that system so that we don't reach that tipping point. Let's protect it so we don't get pushed over the edge where we're constantly constrained in this area, and we're always come back to our existence of our system. Whereas for the ecological concept, we'll see that, well, no, we can't. I mean, while we have been changing this is part of the reason why we see these changes, because we are changing thresholds and moving systems into new equilibrium states. But this is natural part of the ecological system. The intermediate disturbance hypothesis, right? Where too much, not good. Excuse me. So from an engineering perspective, and this is kind of the engineering definition, resilience entails functioning and delivering of services during or quickly after a disturbance. And this is similar to the ecological and evolutionary perspective. But engineering design has been focused more on robustness, so not so much resilience. So you think about a piece of infrastructure, you can have a robust structure so that it can withstand disturbance or multiple disturbances and remain functional. I think in engineering, a lot of that term is thrown around as resilience as well, which I think leads to a lot of confusion. It's really robustness that we're talking about with that. So it's important to have robust assets, and they can be part of a resilient system, but they can't themselves be resilient. So that's why I talk about a culvert. You make your culvert larger, you've got a larger culvert. Okay, it's more robust, but it's not resilient. It just doesn't work that way. For both systems, for both ecological and engineering systems, there's these apply more or less. There's self-organization to the systems. It's focused on an outcome or an endpoint. So from an infrastructure perspective, our physical infrastructure is adapted to climate variability and change. So it's the design is going to represent an adaptation, kind of in an evolutionary sense, that allows the infrastructure to survive. But there's key. This is not a Darwinian process. This is a Lamarckian process. Right? We're inheriting acquired characteristics here as we move forward. So, which is still allowed in evolutionary theory. You could have that. Pardon me. So there's not a steady state equilibrium to return to, but the system's going to find a dynamic equilibrium again, and we're hoping to preserve structure or process or function or ecosystem services, which is what we now call it, so it has an economic value to it. So again, these are kind of common to both, and you can start to see where, I mean, it's hazy in my mind anyway at this point in terms of this. But so here we've got our key characteristics. Now, I include this one because you start to think about in terms of infrastructure and the definitions of infrastructure. Some of the things that characterize infrastructure, are part of important characteristics resilience. So infrastructure systems are inherently have some way to be resilient. There are these aspects of it. So when thinking about designing systems, you can think, if you think in terms of systems, it then becomes, I think, easier to think about how to keep these systems resilient. I'm going to talk about adaptation. before I forget, if anybody wants to see my sources, let me know. I'll send you a bibliography of the sources I use for this. All right, so let's now move from, we talked about sustainability, resilience, let's talk about adaptation. So now everybody hopefully understands the difference between adaptation and mitigation. I think this is a common thing that's still not fully understood by the general public, but even a lot of students I find don't, when they come in, they don't understand this distinction. Of course, adaptation, things are changing, we're committed to a certain amount of change, we have to adapt, it's going to happen. Mitigation is prevention, so we don't get to where we don't want to be. So the IPCC, the Intergovernmental Panel on Climate Change, defines adaptation. So it's an adjustment in the natural human system in response to actual or expected climatic stimuli or their effects, which moderates harm or exploits beneficial opportunities. It's often forgotten. There is good stuff coming too that we need to take advantage of. Longer growing season. Joel, what else is there? Comes good. It's coming. But you can kind of see where these ideas of resilience are built in and adaptation. There's a real strong connection between ecology and ecological thinking and adaptation of infrastructure, quite frankly. So there's different types. So we think about anticipatory, planned, and then in a group called autonomous, progressive modification, and reactive adaptation. And I'll talk about these, and I'm going to talk about how we might implement this from the perspective of stormwater. So this is anticipatory. We just build right now to meet the design performance for the lifetime. So we include our climate change projections now and what the future is going to be like. So for the culvert, we design and construct. So we have the capacity for climate change over the life of the culvert. That's a lot of what's being done now. We have our new projections, we design to it. Problem with this is, it could be a little more expensive, but beside the cost is the uncertainty with the projections. So it could be over designing. For a culvert, it might not be a big deal. But when you think larger systems or larger pieces of infrastructure, this can make a big difference moving forward. And I'll talk about uncertainty later because that's the key, in my view, the key issue. Planned adaptation. You plan an upgrade, that you progressively adapt the design as climate change occurs. The key here is that you allow for adjustment later, and you can make your decisions based on updated climate projections, so you reduce uncertainty moving forward. And so for a culvert, we're going to design and construct the culvert to meet something, say, 20 years in the future, and then we're going to add a second culvert later, depending on how much of a change we're starting to see, what the pattern is, and what the new projections are. But right now, we'll take out some easements and know that, well, when we have to build that new one, we know exactly how it's going to go in, so it reduces future costs, and so there's that planned aspect to it. So that's another approach that's taken. And again, note that for design of infrastructure, these things are currently being done. But when I talk about this, the question is that really resilience? It's adaptation of a piece of infrastructure, but is it really a resilient infrastructure? Autonomous adaptation, progressive modification, those are big words. Redesign, reconstruct as required in response to verified climate change. So we know we're maybe building things to shorter lifetimes. And so instead of 50 years, let's design something for 15, 20 years and update it, knowing we're going to do that, right? Which can help with costs. So for our culvert, again, we can construct it based on existing conditions, and then we upgrade it once we determine, okay, well, now we're seeing this level of change, let's upgrade our system. So really, it's just shortening the design life of these things. These are all perfectly valid and good approaches. Autonomous adaptation, reactive. Well, just accept the damage and fix it. That's another approach, right? You do nothing. So We construct based on existing conditions. When it fails, we replace it. It's a bit risky, especially if you've got, it's not something, for engineering design, if you have, a small culvert that doesn't concern a main road, like the Trans-Canada Highway, where if you have a washout, you're cutting people off, or other aspects. Like the image I showed of the bridge in St. Albans, and that cut people off until they can repair the bridge. Those, you can't do that with this. I don't think, anyway. All right. So given that, the thing about that's adaptation of designing of piece of infrastructure assets, really. But even adaptation is not just a local thing. It's nested within linked with governance, and it's linked across scales. And this complicates things quite a bit when thinking about this. And adaptation to climate change is just part of the process. And it's a kind of response that demonstrates resilience. So the key point here is that adaptation, is a way to be resilient, but doesn't necessarily mean you have resilient infrastructure. It's just part of the whole process of building sustainable, resilient infrastructure. And again, like I said, this way I'm thinking about it is not a Darwinian. It's evolutionary, but it's a Lamarckian evolution. And I think that's a useful way to think about it. All right, so I'm going to kind of talk about this more in a way to get it a little more quantitative, although I'm not going to give you any equations or anything like that, because that will put everyone off. So these are some images of a fitness landscape. So I studied my master's in biology. I studied ecology and evolutionary biology. I remember talking about adaptive landscapes. This thing was Sewell, right? Who came up with this originally. There's a few things. So these are the peaks, right? So this is a one-dimensional one. The multi-dimensional one is more interesting. So if an organism or a species is here, there's a more fit state here, but it can't get there because there's a valley. So how does it get from valley through the valleys? Okay, that's an evolutionary problem. But I remember my professor Ton said that it's easier if you think about this inverted. Flip it over so that you know that you're rolling into an adaptive peak, and it's hard to get out. Once you're well adapted, it's hard to get out. And if you start shifting the landscape around you based on environmental change, climate change, that leads to potential impacts, right? But I like to think of infrastructure, and I like to think of when I'm doing, because I do watershed modeling and I do stormwater. So I'll think of the watershed and the stormwater and the infrastructure, the system, in terms of a landscape, a resilience landscape. And I'll talk about one piece, but it's multidimensional. And that's really, I think, really important when talking about resilience. So if we look at a resilience curve, so this is one way we quantify this. So we talk, in this case, we've got system functionality, full functionality. So we're moving at 100% functionality. And then, we have an extreme storm and we have failure. Think of the image I sent of the culvert that collapsed in that community, right? So resilience is, well, how quick do we recover, right? So let's say, well, option C is in some ways more resilient because you're coming back and you're be coming back to functionality much more quickly, but it's not quite as good as it was. So the best option here is A, where we're more quickly going to full recovery, and we're back at 100% much sooner. Again, there's costs that weigh into this and a lot of other things, but this kind of illustrates how this might happen. So say this is where we are now. Now we go in and we increase the size of the culvert. We have our extreme storm, but we'll still have damage, but we don't have complete failure. And so in this case, we've got our same three options depending on what you do. So you can, obviously it's a lot more quick than if you had full failure, a lot less costly, and you can get to recovery maybe sooner. In this case, you can recover really quickly, maybe not to full capacity. These are clearly hypothetical. All right, so let's look at here. So now, if we take a watershed approach or a system approach, and I think this is where nature-based solutions really come in. And this is I've got a project in Pooch Cove I originally wanted to show some results, but we don't really have, we've got some vulnerability maps that show where some of the infrastructure is more likely to flood under current conditions, and how that changes when you include climate change aspects with the updated IDS, things like that. I don't have those to show you, but let's say, you know, instead of allowing developers to come in and clear cut an area, you force them to keep a lot more trees on there, so it's going to keep the area more forested, and you're going to use your natural forest to help control your flows. In this case, you know, we have a lot less damage because we've controlled those flows on the system-wide scale. So of course, I'm thinking one culvert here, but if you think about a full system, you can see where this, when you think about a watershed, you don't look at one culvert, look at your entire system together. In this case, there's only one option because it's not that much damage. It's pretty quick to fix it, pretty cheap, and you're good to go. Well, now let's say we're losing some functionality due to climate change. In this case, I'm saying we've increased our culvert size, but over the years, you know, the storms have gotten larger. Now our design is really not quite applicable. So we're more likely to get failure again. And we're more likely to not be able to recover because the point is that if we go back to the functionality pre-failure, we're still not doing too well. But if we wanted to get back to meet the current standard, it's a lot more expensive. This is why when I think about just increasing culvert size, it may not be really not necessarily resilient. And then this is, of course, we've got our planned upgrades. So if you come up, and this is one of the things we're trying to do it with Pooch Cove, is the first step was identify their most vulnerable assets, most vulnerable areas. So they'll put in, they'll help replace those. But what we're trying to do is say, okay, these are your vulnerable areas. This is what you need to reduce flows. How you do that is up to you. You can do traditional methods. You can increase your culvert size, whatever. But let's think about nature-based approaches, slowing down the flows, putting in bioswales, collecting rainwater, or whatever the case may be, so that you're not only protecting that culvert, but you're also protecting everything along that same drainage pathway. So you start thinking about the entire system altogether. And I know this is just one culvert, but that's the way I'm trying to approach this. There's again, the work I'm doing, I don't have a lot of results because everything's just starting to get ramped up. But really, that's the goal. And what I see as the biggest obstacle is uncertainty. I've got some time. I'll try and go through that quickly. But if you look at this, in terms of uncertainty, what we're doing when I talked about vulnerability. So we're doing vulnerability and risk management. We have a model. We know what we know. We know we're going to have increases in flows. We can talk about the uncertainty. Go into that a little more. And so we can manage this. We're talking about resilience in the sense of adaptive capacity. Here we're thinking about things we know we don't know. So okay, something's going to happen. We're not sure what it is. So we got to think a little bit differently about it. And then when we talk about sustainability, we're in a different kind of time scale. There's a book, I can't remember the name, a recent book. I haven't read it, but I've heard parts of a podcast on black swan events and don't talk about that too much. All right, so let's talk about uncertainty. So tell me, what's something of which you are certain?
Of course.
Besides George.
I was going to say sexes.
Besides that.
I suppose I'd say I'm uncertain.
That's like Socrates, right?
Yeah.
I'm very certain that I don't know anything. But the point is
Oh God, no.
For me, uncertainty is how we talk about it, how we approach it is the key issue, especially when trying to deal with the resilient infrastructure, because all the stuff I talk about is great, but we don't know everything that's going to happen, and I'll talk about it. We don't know what people are going to think or what they're going to want. But again, going back to this, and I'll just say it. This is often attributed to someone recently deceased war criminal that I will not name because I don't. But it came well before him. This characterization, and this is my little commentary on being annoyed when people attribute it to him. Anyway, this is what we got. Known knowns, what we know. Simple. Known unknowns, what we know we don't know. That's actually pretty straightforward too. Unknown unknowns, what we don't know. Those are the big ones, right? Those are things that are hard. Unknown knowns. That sounds weird, doesn't it? But think about this in terms of a community, right? So this ties directly in with, especially with engineers, when they're working with communities who don't have any technical understanding and knowledge of models. Folks don't know that someone else knows about this stuff. Right? And this actually, to me, is a big part of the problem. And this is kind of where I'm trying to do more community-based stuff, and this is where I'm kind of headed with this. So when I think about uncertainty, I think about it in kind of one of two ways. They're linked, but they're a little bit different. One way to think about it is in terms of surprise, where we don't want to be surprised by an event that we didn't know was possible to occur. Oh, God, we had no idea that was going to happen. And the other way is in terms of ignorance. So we just don't want to make a mistake because we were wrong. So we didn't know something, so we're wrong. I mean, it's similar, but there's subtle differences here. And I won't go into all the details of that structure, but the key here is that uncertainty is the state of things, it's how we function. But it doesn't mean we don't know anything. And it doesn't mean, it means we can accept our ignorance and work with that. It's what we do all the time. So while it's, being uncertain is to be a little bit ignorant, we also know that we know something. So we have some knowledge, even though it might not be complete knowledge. And I think this is an important thing. And as I move through these last few slides, it's in communication with some certainty that I think is key to successfully doing these, on both ends, from an engineering perspective, for the technical side, and for decision makers and community members to talk to each other. With work I've done, I've gotten a lot of flack when I start talking about uncertainty because some of the I don't want to overgeneralize, but engineers I've worked with have been, don't let them know about the uncertainty because then they're not going to trust us. They're going to think, we don't know what we're talking about. We don't know what we're doing. And that when I got that, I was very surprised, quite frankly. And then I'm also part of, so there's this infrastructure resilience professional certification program for engineers. And I'm helping them on the advisory committee to develop the course in climate modeling. And I made the same point about uncertainty in one of the meetings, and I got the same kind of response. My experience, people, you start talking about uncertainty, people shut down, they don't want to hear it, they don't trust you, and it's like, well, that's a problem. It shouldn't be that way, and we shouldn't be afraid to talk about uncertainty. So I'll give you this stuff that I'm talking about is, I'm writing a paper on this. so I'm kind of working through it because I want to gear this kind of stuff so that we do start talking about uncertainty to embrace it, right? But let's talk about different levels. So sources of uncertainty, we've got, this is more aleatory, so natural variability, things that are inherently variable, whatever that means, and then what might be called objective uncertainty, like in just observation data errors and things like that. And then you've got epistemic uncertainty, concerning what we know, what our knowledge. Ignorance, lack of knowledge, prediction error, and subjective uncertainty. They're all somewhat subjective in some sense. Like Niels Bohr's quote there, about prediction being hard, especially about the future. Anyway, these are kind of the broad categories, right? So let's look at climate modeling, right? So we separate natural and internal variability. This is just from in nature. It's natural variability that we, I guess, I don't know if you believe that we knew everything about everything, then we'll be able to eliminate all that. Or I don't know if that's, I personally don't believe that to be the case. Systems, even with chaotic systems, that's not the case. Anyway, then we got uncertainty due to the emission scenarios, and then our model uncertainty. I find this graph is really cool because you can see how our emission scenarios, there's not a whole lot of uncertainty when talking 20, 25 years in terms of infrastructure design. Those are a lot of times our design windows. So these are really not that hard to deal with, quite frankly, from an engineering perspective. But let's zoom in a bit. So if we look at it, so this one is relative, right? So this is our relative uncertainty. So this is our more quantitative uncertainty, where you can see, again, how our natural variability stuff is more or less constant. So we're not going to know any more than we know about that. Our models are over time this gets reduced, but there's still always going to be some model uncertainty. And this is our largest uncertainty. But there are ways to deal with it. This is well quantified. Nothing that we should be afraid to talk about to anyone, quite frankly. And of course, as engineers, this is what we're looking at. Our probability distributions, more hot weather. This is the probability distribution for precipitation. There's always more light rainfall, so we get a lot more light rainfall events than heavy events. But we're getting this shift, and with climate, we're getting a lot more rainfall. It's heavy, which has clear implications. But anyway, this is quantifiable. We're easy to understand. I think easy to communicate, and not something that we should be afraid of talking to anybody about, because engineers have the tools to deal with this and know we know how to do this. And so this is a manual practice from ASCE, characterizes the same things of what uncertainty the way I did, just a little bit differently. So we look at recognized, well-characterized uncertainty, recognized but moderately characterized. Notice how it's very qualitative. This is from an engineering text. So this is what is poorly characterized, but again, we recognize it, we can't characterize it. And this is from an engineering perspective. We don't know what they're going to do. And then we just simply don't know. So one of the projects I have now, this is from my discovery grant, and I'm kind of breaking the uncertainty out. And this is where, honestly, Joel, you and I were talking the other day about some of this. This is where I want to go, and I think this requires a strong social science input. Anyway, like I said, scientific uncertainty, and I'm thinking about this in terms of Newfoundland and Labrador. It's not unique to us, but it's a little bit different than traditionally thought of. So our scientific uncertainty, like I said, is well defined and quantified. We've got our data, knowledge, response model, and everything. This is relatively straightforward to deal with. Simple. In the problems, we've got what I'm calling capacity uncertainty. Well, the typology is a little novel. The content's all there. We don't know what the policy is going to be. This is what a lot of the municipalities are faced with, right? We just don't know, how much funding is going to be out there. How's the economy going to be doing? And from some of the work I'm doing is about getting at this level, in the sense that if you know what level of funding you have, you can then determine what level of science or technology can be applied. And the goal is in the research is to try and find your best case. This is the best we can do. Okay, so how close can we get to that with limited resources? This way, folks will know. Okay, well, I have this much money, this many people. We can do this, and we'll know we'll get a reliable answer. That's one of the things I've been starting to work on now. And then this one is what I'm calling community uncertainty. And this is about local knowledge, lived experience, how people are going to deal with uncertainty, how they deal with risk, and how they want to manage it. This is something that I have no qualification to deal with. But I recognize it, and one of the things I want to do, and I'm hoping to get going sabbatical next year, and I want to do looking into one of the things doing a community-based design project. Get folks in here, and I know it's been done in other places. It's been done in New York City, It's been done other places, the very thing, but they get people at the table. We need to do this. How do you want to do it? And the engineers respond to that. Does it, how does it work? But that's really the only way to get at this, but if you talk about, okay, no, the science, we know it's uncertain. Don't, it's not, we don't know. I know there's, well, it's easier said maybe than done, but I'll stop. Yeah, so just as a final thought. So even our well-characterized uncertainty is not always easily quantified. So I don't know if you've heard the term deep uncertainty. That's what this is referring to, and there's lots of decision theory out there, but one of them it's called info gap decision theory, which deals with this deep uncertainty. But when we talk about our qualitative uncertainty, we don't know at all levels how they'll choose to deal with it, and then we need to include modes of knowledge from local stakeholders and how communities want to manage uncertainty and what their risk appetites are and things like that. So. So the process is what matters, how we do this. So in my view, if you have a good process, then you're going to have a good outcome. If you do it right, you're going to be in a good place. And maybe that's working on faith, but that's how I've kind of lived in my life is, okay, if I work hard, do this right, everything will work out. Maybe that's how I got here. I don't know. It's possible. But yeah, and the technical term is satisficing. So satisficing, like these systems, they can't be optimized. Engineers like to talk about optimization. And this is another thing that I've got. Well, I have students, potential students. I talked to one last week, and she was talking about her optimization techniques. But that's not going to work when you have a lot of uncertainty. So satisficing is about having something that works. It's very pragmatic. Yeah, so this is a big thing. Uncertainty is an opportunity. We have a chance to be creative, do something different. So it's not something that should be shied away from. This is my last slide because really the biggest way forward here is through scenario analysis. Just as they do with climate change projections, you look at scenarios, ways that you can alter that resilience landscape through, and again, this would be using models, the technical approach, but it's more than just that. So yeah, that's it. Hope that was useful.
We have a couple minutes for questions. Yes.
Yeah, thank you so much for the really exciting talk about infrastructure. So I'm an archaeologist, and I really liked how you began your presentation with some ancient infrastructure. And one thing that stood out to me is that all of those civilizations are gone, usually because of some failure in their infrastructure. But my biggest kind of question or issue, I guess, with it actually goes with your evolutionary thought process or analogy to infrastructure, be it the Markan or the Armenian or whatever. I'm not sure if that is the best way to think about it, because there is no death, there is no extinction. Things do not die. We have things from 1 million years ago. We have infrastructures from thousands of years ago. And, it's one thing to kind of think about like functional or not functional, 100% to 0%. But failed infrastructures continue to function. They just continue to function in ways that we did not predict or did not want or did not hope. And actually, I really also like your culverts, because I've seen many failed culverts this past summer. And sure enough, they don't provide the flow of water. They create miniature lakes, which are very, not very comfortable to walk around. Or failed, dams still impact water flows. Failed nuclear power stations continue to emit radiation. So, there's kind of this unwanted afterlife of infrastructure that I think it needs to be also kind of considered, especially when we're dealing with things like climate change and systemic infrastructural failures in a lot of the stuff we have today.
Yeah, I don't really have an answer, but I appreciate the thought because yeah, I do know that the evolutionary analogy breaks down in a lot of cases, again, because there's not a Darwinian component to it. But like you said, there's not depth. I mean, I could argue whether that like in your Roman some of the fluctuations in that you could follow with climate change in Roman civilization, or the expansions and contractions of the civilization that ultimately led to the death of. It's not, but that's just it. It's not about the one piece of infrastructure, right? I'm just thinking out loud here. It's about the entire system and how each piece will function within that system. And if you have a failure over here, the rest of the system might be robust or resilient enough to continue to function. But if you have enough failure, you have complete failure. Something definitely to think about.
So we talked about uncertainty, and I was curious, how do you approach communities and policymakers with that, like about such difficult subjects with uncertainty? Bring them, and you're supposed to be the one with the answers.
Yeah, I don't have a whole lot of experience doing it, but I try. I honestly, this is just the thought is like with humor. Quite frankly, you're fallible, and then you admit you accept that. I think people would be more open to it. Like I said, that's just, I might be completely wrong about that, but that's kind of how I've approached it. In my limited experience, it's had some success because people will relax a bit when you can make fun of yourself, really. So.
Maybe one, if it's quick, we can go one more. Arn? Yeah.
Philosophy and culverts. Yeah, I mean, right at my alley. Could have been better. And I don't know. It sounds like you're almost looking for more input on the uncertainty and planning piece.
Yeah.
And I would urge you to look at some of the work in science and technology studies, particularly the participatory STS. So it kind of gets at this question. In fact, in Geography 6000 next week, we'll be reading a piece on doing flood risk differently.
That's what I got. On that paper,
and
so that's why.
a lot. So, but with specific reference to the kind of philosophy of ignorance or agnotology and whatnot, Matthias Gross, who's a sociologist of STS, Ignorance and Surprise, is one of his books, talking about doing environmental restoration, but with community input, knowing that you're creating future environments that you are not going to be able to fully predict or remediate and what have you. So, yeah, I mean, I think it's a central challenge, but there's a lot of really cool work in that STS thing.
Yeah, and it's exactly one of the things that I'm looking for help, to develop some of my ideas, to bring it into engineering, to bring it over, to get folks, engineers, students, and even practicing engineers to think a little bit differently about this stuff.
All right, please join me in thanking our wonderful Evan, did you just want to quickly mention about Thursday?
Yeah. So on Thursday of next week, we have the pleasure of two guest speakers from the Architect Corporation, Chief Legal Joe, and the Forestry Manager, Greg Major. They'll be giving a public seminar at 2 p.m. in the Science Building 2109. That's the Great Big Lecture Hall on the property. In addition, they're running a student workshop from 3:30 to 4:45. So I encourage all the students who haven't signed up for it, please do so. That is for, there's a limited number of spaces